Welcome to Chapter 12 of Research Methods for Exercise Science and Sports Medicine students. Let me get the PowerPoints up and we will get going. Finding differences among groups. Right. So hypothesis testing. So we can do inferential statistics, which makes inferences about populations from research on population samples. We compare groups of individuals who differ based on a treatment group and a control group. All right, so a treatment group could be they get, we track people, give them all the same calories. We have some folks exercise and another group doesn't exercise. And then we can measure body fat, muscle, lean body mass, maybe strength gains, so on and so forth between the two groups prior to doing the study, and then have them one group exercise for 3 months, the other group doesn't, and we can measure again 3 months later and see what the differences are, right? You could do that with diets, all right? One group's on a specific diet, another group's not. We could do it with supplements. We could even do blind control on the supplements where both groups thinks they're getting a supplement. We have them all go work out, have them do everything else business as normal, and see if there's any change with the group that's on supplements versus the group that's not on supplements. So again, creating null and a directional hypothesis. So the null is groups do not differ on dependent measures. Treatment control groups score the same on balance test after 2 weeks of training. Again, sometimes that's what you're looking for, right? We're looking to see that everybody turns out the same, right? So, you could have a group that doesn't go on any specific diet, a group that's on keto, a group that's on intermittent fasting, a group that's on a detox, a group that's on, and we just control for all the calories, right? So all the groups are different. The control group is the no diet, except for, we'll just put everybody at 2,000 calorie go, and we have them go for several months, and then we see what happens. And again, I would go with the null on that I think all groups under the same amount of calories should see pretty much the same results, right? When it comes to weight loss or weight gain, things like that. Directional, the groups differ on dependent measures. So the treatment group scores high or significantly higher on a balance test than control group. Or, we have certain type of exercise mode versus another type of exercise mode, and we look at the differences in strength gain or the differences in endurance, or whatever those differences are. We expect to see a difference between the control group and the group that's on a different workout regimen, right? Or a group maybe that's getting a supplement versus a not, like control, not getting a supplement. All right, so selecting appropriate alpha levels. We talked about this, but type 1 error is a probability that the true null hypothesis is incorrectly rejected. Chance that the group differences in a sample are found when in fact the treatment does not cause the effect, right? And the difference is due to the error, right? Alpha levels selected before data collection, acceptable change of error, generally accepted 0.05, 0.01, and 0.001, right? And again, it's, typically you see a 0.05, but there are some that are more strict, right? So again, making a decision regarding the null hypothesis based on calculated stats. Make objective decisions about statistical differences. Decisions are phrased in relationship to the null, and you compare alpha level to calculated probability level, right? So again, with the alpha level, we're just saying that, if it's at 0.05, there's only a 5% chance that anything you see, any difference in there that you see is due to error, only 5%, right? The 95% is your confidence interval that whatever you did during the experiment, whatever the experiment versus the control, that was the actual change, right? Or 0.01 or 0.001, right? So decisions to reject and null means that the real difference exists between the groups. So if a 0.05, you know, if you have alpha at 0.05 and your p-value comes in at 0.049, you reject the null, right? So your p-value comes in, it's below 0.05, right? So there's less than 5% chance that there was error. You met the alpha, you're good to go, right? So we're going to reject the null. Now, if it's 0.52, which is really close, but you didn't make the alpha, right? Even at 0.52, you didn't make the alpha, okay? And at that point, we do not reject the null, right? So it means that it's not, you know, there's not enough statistical difference to show that the null doesn't exist, or that there was an error that caused any differences that might have been seen, okay? So if we want to interpret result for meaningfulness, we want to see significance indicates that there was a real difference between the groups, okay? And so when you hear these words, significance and meaningfulness, they're not, you know, it's not that you can say it's significant, it's meaningful, and that's the same thing. So you got to understand that significance indicates that there is a real difference between the groups, and meaningfulness indicates the strength of that difference, right? So the more meaningful indicates there's a stronger difference. Significant means that, hey, statistically you met the alpha level with the p value and everything, you're good to go. Meaningfulness means like there's a real change, or there's a real difference between them, right? And the stronger, the more meaningful, right? And we calculate that as effect size, right? So we talked about effect size earlier in the last chapter, right? So a t-test, right? We're going to start talking about some of the different statistical analysis we can do. All right, so a t-test is going to compare two groups on one independent measure. Oh, excuse me. So it's simple, easy, quick test. You'll see it written as a lowercase t, right? So you'll see t equals whatever, right? And again, the calculated t must exceed the critical t. So p-value, again, has to be less than the alpha level, all right? So student t-test, does a sample differ from the larger population on the dependent measure? And can it be used only if prior population data such as age or gender or norms exist? The independent t-test for two groups, do two groups differ from each other when one has an intervention and the other does not? Right, so again, you've got a group that's getting the treatment and a group that is the control. The groups must be independent from each other. So you have treatment control, or children versus adults, men versus women, however you group that out. Okay, is there differences? The dependent t-test for the two groups, does a sample differ from the pre-test to post-test? The two groups matched on criterion characteristics differ after one group has an intervention. Okay, so basically your matched pair or paired sample is the groups were similar coming in, right? So they're similar coming in. So independent is groups are different, right? So men versus women, children versus adults, tall people versus short people, you know, fit people versus out of shape people, however you did it, okay? The dependent would be groups, basically everybody got randomly matched into two groups. So now the groups are randomized, they seem very similar. And now we're going to give one group a treatment, one group gets the control, see what changes over that time, okay? Meaningfulness of a significant t-test. Given a significant t, what is the strength of the differences between the groups, okay? Cohen's d is measure of the effect size. So rule of thumb, small is 0.20, medium is 0.5, and large is 0.8. Okay. All right. So analysis of variance, or an ANOVA, is used when more complex experimental designs where you have more than two groups to compare. All right. So again, say we were doing a no diet group versus a keto group. All right. We could do a t-test. All right. So the no diet is your control, your keto is your treatment group. Now let's say we're doing no diet versus keto versus low fat, right? So now we've got more than two groups. We have more than one dependent measure. So again, we could measure, we could either have more than two groups compare. We could look at different things such as weight and body fat. We could look at weight, body fat, adherent, like adherence, however you want to do it, or you have more than two groups and one dependent measure, right? So we could have, we've got three groups and we're all looking at weight loss, right? However it is, okay? When we look at those, you're going to see the statistics going to be in F, right? So again, the letters just mean, letters basically tell you what type of statistical analysis they did, right? So if you see a lowercase t, then we know they did a t-test. If you see a lowercase r, we know that they did a correlation, right? You see a lowercase f, a capital F, we know they did a ANOVA. So again, you want the calculated F to be greater than the critical F, and the p-value, again, needs to be less than the alpha level, right? So one-way ANOVA is the most basic format of an ANOVA. You have two or more groups with one dependent variable, right? So again, could have all, like 3 or 4 diet groups, and we're just measuring weight loss. With 3+ groups, post hoc tests necessary to determine which groups differ, right? So again, this helps you to look at the differences between each individual group in a way, right? So the no diet versus the keto diet, no diet versus the low fat, no diet versus the intermittent fasting, and keto versus intermittent fasting, keto versus low fat, so on and so forth, right? So this is what a one-way ANOVA table may look like. So you're looking at the F value versus the critical F. So the F value at 7.83 is greater than the critical F, which is 3.35. So the decision is reject the null, right? So there is a statistical difference. And the p-value, if you look at that, is 0.002. I don't know if it shows the alpha on this, but we could probably just assume the alpha was a 0.05. Even if it was a 0.01, we would have been fine. If it was a 0.001, we wouldn't have been any good, right? But as long as we're at 0.05 or 0.01, or whatever they wanted off the alpha of this one, then your p-value is fine. It's below the alpha level, right? So repeated measures ANOVA are used when dependent variables measured more than once within the group, okay? So you're tracking changes over time in the dependent measure. So again, maybe we check their weights at month 1, month 2, month 3, month 4, month 5. Single group participants act as their own control. Two-way ANOVA is used when you have 2 or more independent variables called factors. So each factor has at least 2 levels, right? Then you're going to use a statistical capital F. So again, same interpretation of F and p-value, main effects, differences within a factor, and the interaction difference. So you have interactions of the different factors, okay? So again, we could be looking at diet and exercise as the independent variables, right? So again, you could be looking at, they've got an example of what is the effect of frequency and intensity on maximum oxygen uptake, right? So again, we're looking at not only how many times a week that they go, but also what's their percentage of their max intensity as they do it, right? So you could do groups. So they got 2 groups doing 3 and 5 days, and groups at working at 65 and 85. And so again, you could have 4 groups in total. To be honest, you could have one that goes 3 times a week at 85, one that goes 5 times a week at 85, one that goes 3 times at 65, one that goes 5 times at 65, 5 times at 85, 3 at 65, 3 at 85, however it is, and looking at those different changes between all those groups. Okay. So again, you look at main effect for just frequency. So you see the R statistic 1.4, but the p-value is at 0.1, right? So it's not going to be statistically significant just for frequency. So it doesn't matter how often they go as much, possibly. But, you know, we're not seeing enough difference. We're not seeing that there's not enough error, that maybe there's not an error involved, right? You know, or there's other factors that are causing any change that we see. Now, again, the main effect for intensity is a 10 on the S statistic, and it's 0.001. And if you see that A, you go down, it indicates the significance is at 0.05, so we're well below, right? And then frequency and intensity, again, we're at 0.045, which means we hit significance at since 0.045 is less than 0.05, you're good there as well. Okay. So again, we see maximal oxygen uptake after 1 month training period based on intensity and frequency. So you get 3 days a week versus the 5 days, and then we look at the intensity. We've got the 85, which is solid. The dotted line is the 65, and you can see that 3 days a week at a higher intensity seems to have the highest VO2. Yet even at 5 days a week, you know, even though it trended down, it's still higher than the lower intensity, right? So again, working harder, whether 3 days or 5 days. Now again, there seemed to be a drop off after 1 month. Now again, maybe, you know, there's a lot of things you could look at with that. There's a lot of questions that arise from that. So if you continued that for more than 1 month, what trend would we see? You know, and again, you know, just some speculation. We could see that it's just overtraining for these folks, and it's just going to keep going down as a possibility. Maybe with them, they, you know, they might not have been training before, so it could be a little bit over the top. So just that much frequency, if that intensity was just too much, okay? Maybe after a while, their body will adjust, and they might see an upswing, which is another possibility. So again, how do you answer those questions? We run a 2-month-long study. We run a 3-month-long study. You do 4 months, 5 months, 6 months. You know, year-long study. You know, I mean, whatever you do. You know, I mean, you use these same parameters of 65%, 85% frequency at 3 days versus 5 days, and we see if there's any change over the year, right? So again, is there, and hopefully what you would see with the second group that you did is something similar to this after 1 month. So again, you know, all right, well, this is pretty typical of what we see in the 1 month, you know, and then you just continue it on and see what changes after that. Because again, something that might be alarming would be to use the same type of population, you know, like a similar sample out of a similar, you know, hopefully a similar population. But if you saw different results after month 1, be a little bit alarming, right? Because what was the difference between that group and this group where we would see different changes, right? So hopefully you'd see the same thing at least from month 1, and then see what happens from there. Interpreting the two-way ANOVA, main effect, significant and specific factor only, regardless of other factors. So different exercise intensities leads to different VO2 max regardless of frequency of exercise. So we did see that. So the harder you work, doesn't matter if you go 3 or 5 days, you're going to have a higher level. Exercising at 85% max 3 days a week leads to the greatest increase versus also, not overtraining in the sense of frequency seems to give you a better a higher VO2 versus the 5 days, at least over a 1 month period, right? Factorial ANOVAs is an extension of a two-way. You have 2 or more independent and 2 or more dependent, right? So the significance is going to be the same as the two-way though. Post hoc test. So ANOVA test indicates that differences amongst groups exist, but do not indicate which groups differ. So you see there's, it's sort of like, you see there's a difference in there, but there's, you don't know what the difference is, right? So it would sort of be like, say there was a test that could indicate whether or not you had cancer, right? But it doesn't tell you what type of cancer it is. So it's just an overall, like take this blood test. Something in your blood tells the doctors that you have cancer, right? Now, what the post hoc is there to do would be in the same, thinking theoretically in the same regard, the post hoc test would be, all right, well, do they have colon cancer? Do they have breast cancer? Do they have, cancer in the liver? Do they have stomach cancer? What type of cancer? Is it brain cancer? Pancreatic, whatever it is, right? So post hoc test would now figure out where that is. What's the difference? Where's the difference? Which groups differ, okay? So tests are on a continuum from conservative to liberal in detecting group differences, right? So these are the different post hoc. So you got the Sheff, the Tukey, HSD, Newman-Cools, and Fisher's LSD, and it's not the, you think the LSD is the most liberal, it kind of makes sense, sort of if you wanted to memorize this for a test, just remember folks that are a little bit more liberal in their drug use, like LSD, way to memorize that. But yeah, the Sheff is the most conservative, the Tukey, the Newman-Cools is being more liberal, and then Fisher's LSD, all right? An analysis of covariance is what we call an ANCOVA. All right, so we've done ANOVA, now we're on to ANCOVA. So statistically controls for covariance that may have an impact on statistical outcome. So age, initial blood pressure, BMI, you're looking at multiple things that may have a statistical impact on what the outcome is, all right? So this allows for statistical control when other methods of control are not possible. Yeah. That's that out of that chapter. Again, not really long chapters when we're getting into these. Again, part of that, the reason for that is they don't want to over inundate you with too much of the statistical. All right, so each one of these is going to get a little bit more focused, not as general as the first chapters. But hopefully you guys are getting an understanding of this. Again, we're not going real in depth on these. We're not doing any practice ANCOVAs or ANOVAs or t-tests. But again, as you guys read through the research literature, the articles I'm assigning as well as any other ones, hopefully you're practicing going through and trying to understand the method sections and looking at, so at first I wanted you guys going through and making, when we're explaining bias and things like that, seeing if you see any bias in the way that people are analyzing, or creating the experiments, right? Are they giving any special preferential treatment or anything like that to one group versus another, right? So some of the examples I told you guys to look, because I've had you guys look at a lot of diet stuff, is, are they controlling for calories in one group and not controlling calories in another. I've seen that type of bias in many studies. Okay, you know, as we're getting into looking at the alpha levels and things like that, you know, are people getting their analysis, or are they doing their statistical analysis, and are you seeing them come in under the alpha levels? You know, whether you see it as the p-value, the r, so on and so forth. And if so, great. If not, how are they explaining that out? Because again, I've seen folks that are not getting statistical significance, and they'll still try to say, yeah, but there's still a difference. Yeah, but, and again, that's why the stats are there. It's to call you out, to say, look, there you may see a difference, but we can't rule out that there was some error or bias involved in seeing that difference, right? So again, as we go through this stuff and you learn more, go back to some of those old articles that we looked at and see what you've learned now, and then reanalyze them and then give it a second go. All right, and see if your analysis of what you're seeing has changed. All right. All right. I'll see you guys on the next chapter, and this one is done.